So today in physics, we are going to introduce some things, and from here on out, this is kind of the types of problems we're going to be doing. So we're doing motion. Motion graphs is what we've been focusing on. So the graphs that we've been analyzing, you actually made one on Friday. Okay, you rolled a marble, you collected some data, based on the data, you put it in your iPad, the iPad, you told it what to graph, boom, you got your graphs. The conclusions that you were able to draw, fingers crossed, from your motion graphs are very similar to the ones that you've been analyzing. Okay, so we've taken two progress quizzes, one on position versus time graph, one on velocity versus time graphs. They're two different things. My intention is to give you a quiz in class on on Wednesday. Two different quizzes, one on position versus time, one on velocity versus time graphs, where I'm going to go through and I'm going to put that in S1, our first standard, which is 1D motion. So can you analyze and interpret those motion graphs, both position versus time and velocity versus time graphs? I gave you those progress quizzes for you to go through, try. I have some extra copies if you want to try it again and pretend like you've never done it before. That's an option for you. Also, the answers are posted in the agenda for those days, whatever days those in particular were. Today, we're going to start talking about problems, story problems, and that's what kind of from here on out to the rest of the year is going to end up being, is a lot of these types of story problems. So there's a method, there's a process that I kind of do, and I'm going to try to teach you the best that I can, and then it's going to be a lot of the same, and you identify, and then you put it in, and you kind of figure out what we're going to use and where we're going to use it. So that's what these half sheets is your formula sheet for this unit. And actually for the first 2 units. These are the 5 equations we're going to use for the next 2 units. I don't expect you to memorize these. I do not expect you to memorize these. I will give you these, or you can, you might memorize them, but these are them. In order for us to use these, we should probably make sure we know what each of these variables represent. And that's what I have on the board. So I told my last class, I think this would be a good thing for you to write on the back side of this, just kind of for a reference point, that as we're going along. Until you get good at them, then you won't need it. But then you have it for reference. What we're going to write on the board today is not something I'll give you on a test. What you have in front of you on that yellow sheet, I will give you. I don't expect you to memorize this. This is stuff I expect you to memorize it because we're going to use it enough that it hopefully will become pretty second nature. So there's a couple different terms that we're going to use. And there's a bunch of variables on these equation sheets that are going to go through and they match. So some of them represent the same things. And units are going to be important. So when we go through and we have a number with a unit next to it, that will help us identify which of these they are. And then the idea of the questions asked is, so when we talk about variables, that's what we're going to be looking for. No, I'm sorry, I wasn't talking about variables. Questions asked is when they say how fast is it going? Well, then that's going to be a velocity. To kind of help us with that. So I'm going to kind of do one color for each line just to kind of help visually keep it separate for you guys. But that's what we're going to do. So terms, displacement. Displacement and distance are very similar, but displacement is a vector quantity. And it's derived from some random, I shouldn't say random, some predetermined origin point. So here's 0, and how far is everything from this measured point is 0. It's got positives and negatives associated with it. The units, or the variable that we're going to use on that yellow sheet is going to be a delta x. Now if you look at that sheet, there's delta x's in some of them, but not all of them. There are times though, in the near future, that we're going to be talking about displacement, not in the horizontal in the x direction, but in the vertical in the y direction. So we don't have a separate list of equations for the y direction because they're the exact same equations, but instead of using delta x, we write delta y. That's it. It's the only difference. When we measure distance or displacement in this class, positive and negatives tell me directions. The units that we're going to use represents meters, which is simply an M. So parentheses is the abbreviation for our unit. So meters is measured in M. The pretty standard question that will be asked is something along the lines of like, how far, I don't know why we'll just go, like, how far did the car take to stop? How far did it take for the car to reach that speed? Okay, that's a general question, not the only question that can be asked, but it's a general kind of, is a good starting point. How far did the apple fall? Yeah. I almost said how fast, but that's definitely not this one. Velocity. There's that amazing song that I played for you about speed versus velocity. Speed is how fast you're going. Velocity is speed and a direction because it's a vector quantity. Remember, vector commits crime with both direction and magnitude. Oh yeah. Thank you. Playing along. So the variables, we use a v. However, if you look at our list of half-sheet list, there's 3 different v's on this list. Okay, there's 3 different v's. So I'm going to list all 3. And we use subscripts to differentiate between my different velocities. So I use vi for initial velocity. I use vf for final velocity. And I use avg for average velocity. Those are the different velocities that I use.
What was the VF?
Final. Okay, so how fast am I initially going? How fast am I going at the end? What's my final speed or my final velocity compared to my average speed or my average velocity? I kind of italicize my I because that's how it's kind of on your formula sheet. That's why I do it. Okay, so these are different units. This average velocity I want to talk quickly about. The average velocity equation, which is that first one, is kind of its own thing. When we talk about average velocity or average speed, it's this idea of like overall, what was your speed for the long trip? I drove from here to Madison over the weekend, and it was 100 miles. I know it's not 100 miles, but for ease of numbers, it's good. I drove 100 miles, and it took me 2 hours. What was my average speed? 100 miles, 2 hours. My average speed was 50 miles per hour, right? That was my average speed. Does that mean my speedometer said 50 every single moment I was going down the road? No. That's what we would refer to as instantaneous velocity. Okay, how fast am I going at this instant in time, my instantaneous velocity? Okay, that is not average velocity. So when I'm going to Madison, I go 70, because the speed limit is 70 for most of the trip. But sometimes I was only going 25 because I was going on some residential roads before I got on the highway. But if we talk about overall the big trip, I averaged 50 miles per hour. Okay, so that's average speed. It's kind of its own unique thing. We don't use that one, that very first one very often. The only time we use that first one if it very specifically says an object has an average velocity of, or what is the average velocity, but we don't use it very much. So a lot of times we're using the bottom 4. So initial velocity, final velocity, but then average velocity. The units that we use, I'm only going to give you the abbreviation for, it's meters per second. It's meters, not miles, because we measure our displacement in meters. Typical question. How fast? How fast was the car initially going? How fast is the car going at the end? Other ways we could word it, but that's a pretty standard way. It's how fast. Time is simply the letter T. I write my T's like that to kind of match the T's on your sheet, but more than anything, I don't want it to look like a plus sign, right? I don't want my T to look like a plus sign. So I kind of make it a slightly cursive T. That's why I always make my T's like that when I write it by itself. I don't here because T for time is a word. Okay, but our units that we in this class measure time in is seconds, which we can abbreviate simply with the letter S. So how many seconds does it take measured in S? Our typical question is how long does it take to get up to 50 miles per hour? How long did it take to go 240 meters? How long, we're talking about time. Now realize that how long could be a unit of like distance, right? Like how long is this table? So you just got to make sure you interpret that appropriately. Okay, so how long? It could be like how much time has passed, how much time did it take? Those are some other things, but generally we say how long. And then our acceleration is the letter A. And there's two units we can use for it. Most of the time, I give you units of meters per second squared is how we say that. It's meters per second squared. Sometimes we'll see meters per second is sometimes what we'll see, which is kind of a, I don't know, you sometimes see it. If we rearrange this mathematically, we get meters per second squared. But what acceleration is acceleration is the change in velocity per unit of time. It's the change in meters per second, so how many meters per second did it change per amount of time, per second. So how many meters per second did it change? We say meters per second squared. All of these, with the exception of time, are vector quantities, so we have positive and negative numbers. Positives tell me directions to the right and up. Negatives tell me down or left. For acceleration, it's pretty straightforward. What is the acceleration is generally what we ask. I'm going to emphasize that units are important because as we go through and we solve problems, there are going to be story problems. And the story problems are going to have some numbers given in the problems, and based upon the numbers with the units listed behind it, that will help us identify what they are. And then which variables do we put them in. So this is going to be something that hopefully you're going to get good at and you're going to be not need to reference anymore, but it's going to be on the back of the sheet. Now I want to look at that half sheet. That half sheet is called the Fabulous 5 constant acceleration equations, sometimes simply referred to as, I call it the Fab 5. Okay, just so you are aware, the equations that they use in traditional physics are slightly different. They're slightly different. So if you talk to someone in traditional physics or AP physics, they're going to be different formats of this. They aren't going to match exactly. The premise is the same, but they're going to be not exactly. These 5 equations, we use them regularly enough that instead of trying to say them like by letters, I just kind of go through and I number them. And I say, hey, this is equation number 1, this is equation number 2, this is equation 3, 4, and equation number 5. Okay, those are the equations that we have. Equation number 1 is for average speed, average velocity, and only average speed or average velocity. We don't use this equation number 1 unless they very specifically give us this or ask for this. The majority of the time, we're going to use equations 2, 3, 4, and 5. Now, part of my problem when I go through and I do these problem solving, I do these, and I set these problems up, I make a list of variables. And I make the list of variables the exact same way every single time for consistency. And it kind of forces my brain to say, hey, I'm looking for these things, and I'm asking very conscious, and making a very specific effort to try to find them. Because in the past, like before I started doing this, it was always like, well, what do I have? I don't know what I have, what I don't know, what equation do I use? And after how many years I've been doing it? I think this is year 14 of teaching physics. 15? This is starting my 15th year, I think, of teaching physics. I've gotten to the point where I figured what I think tends to be the best and tends to give us the most success. So each and every time I do a problem, I make this list of variables, and I list it in the exact same order every single time. Okay, and when we go through a problem or two today, I'm going to do that. And even after doing this for however many years I just said, I still do this. And you say, do I have to? You don't have to. I really encourage you to do it, because it really kind of forces you to think, do I know this? Do I care about this? Am I being asked this? Okay, so if we look at, these are the 5 equations, or the 5 variables that are all in equations 2 through 5. These are the 5 variables that fit in here. Slightly, some are in some are not in the others. And if you look at equations 2, 3, 4, and 5, every equation has 4 variables in it. Okay, it has 4 out of the 5. Now, if we wanted to, we could derive these and say, well, where did these all originate from? But generally, people don't care. We just say, oh, these are the equations? Okay, let's use them. It does talk about constant acceleration, and when we looked at velocity versus time graphs, we always had these nice straight lines, and I said, realize in real life, that's not the case. But those are the ones we're going to focus on. And when we do what I call Fab 5 problems, problems using these 5, they're all going to be what we call constant acceleration, because we can solve them using algebra. If we had non-uniform acceleration, then we have to use calculus, because it's a varied rate problem. So like your first 0 to 10 miles per hour, your acceleration is different than from 10 to 20 and 20 to 30 in a car. In real life, that is the case. But for us, we're only going to deal with constant acceleration, because then we can use algebra to solve. So these bottom 4 have those 5 variables in them, but each one only has 4. 1, 2, 3, 4, 1, 2, 3, 4 different variables. Notice there's a t and a t squared. 1, 2, 3, 4, 1, 2, 3, 4. Now, I'll just say this right now to get it taken care of. Most years I have some students say, hey, if you ask me to solve for final velocity, I got an equation. If you have an equation that asks me to solve for delta x, I got it. But what happens if I need to solve for acceleration, or I need to solve for time? There aren't any equations that have time over here. Okay, so let me just address that right now. Any of these problems, we can solve mathematically for any of the variables. This one happens to be set up for final velocity, but I can rearrange this and I can solve for VI. I can rearrange this and I can solve for A, and I can rearrange this and solve for T. All of these equations can be solved for any of the variables. Okay, we just got to rearrange and do some algebra to get there. But if we go through and we look at our list of 5 variables that I've listed on the board, we'll notice that one of the variables is missing in each of these equations. And by identifying what's missing will be helpful in choosing the equation we're going to use when we try to solve it, of the problem. So if we look at the second equation, we have an initial velocity, we have a final velocity, we have an acceleration and a time, but there was nowhere in that equation is there a delta x. So equation 1 does not have a delta x, or a delta y if we're talking vertical, okay, but these are all for the x direction. So there's no delta x, and maybe you want to jot that next to you. I would encourage you to jot that next to equation number 2. Equation number 2 is an equation that we would use if we have this information and we're looking for one of these 4. There's no mention, or we don't care about delta x at all. It's missing that equation. And I'll show you what that means in a couple minutes. If we look at equation number 3, we have a delta x, we have a vi, we have a t, we have a number, 1/2, we have an a, and then we have a t squared. T and t squared are the same variable, just keep that in mind. But we're missing an equation or a variable, and the variable that is missing here is Vf. So equation number 3 has no final velocity. It has no final velocity associated with it. Now, equation number 3 could be solved, you could solve for t. You could solve for t, but notice there's a t and a t squared. So if we had to solve for t using equation number 3, realize that you might have to use the quadratic for it. It doesn't happen very often, because a lot of times we have initial velocities, very conveniently, that are 0, so 0 times t is 0, we can cancel that t out. So don't worry about equation number 3. It doesn't get, we don't do quadratic very often, but sometimes we do. If we look at the fourth equation, we have a final velocity squared, we have an initial velocity squared, we have an acceleration, we have a delta x. There is no time listed in equation number 4. So we use that one if we don't know time, we don't care about time. And then last, equation number 5, delta x vf vi t, there is no acceleration listed. Okay. So the combination of knowing what variables are missing, using your units to identify what variables we'll put those numbers in, should kind of help us get these problems set up. Okay, so we're going to go through and we're going to do a few of these problems today in class. So we're going to look at the in-class problems, and these are exactly that. They're problems we will do together in class. These are not homework problems. We'll do some of them. We definitely will not do them all. So what I'm going to do, I'm going to go through and I'm going to put the problem on the screen. I'm going to highlight some stuff on the screen, but when I actually go through and I work the problem out, then I'm going to put it on the board. It's just going to be easier for you to see compared to on the screen. It gives me a little bit more space. But I do kind of want to show you what I'm doing when I do these problems. So today I'm going to use highlighters just because I have some highlighters handy. But a lot of times when I'm doing what I'm about to highlight, I'll use like my pen or pencil and I'll underline. So a lot of times that's what I'll do, or I'll circle stuff, and it's really just kind of to help me identify what do we know, what are we looking for. So we're looking for numbers, we're looking for questions, and then there's going to be some implied things in there too that we got to make sure we dig into. So we read the problem first time, just kind of get a general gist of what's going on, then we read it for a little bit more content. So when Jenny applies the brakes of her car, the car slows uniformly, that just means at a regular rate, from 15 meters per second to a stop in 2.5 seconds. How far does it take her to stop? So how far? So the how far, that's our question. That's what we're going to be asked to solve for. Looking for kind of some other numbers. Okay, and again, a lot of times I would just use like a pen and I'd be underlining, but I have the highlighters handy, so I'm just going to use that. Okay, so when Jenny applies the brakes to her car, she slows from 15 meters per second in 2.5 seconds. So those are some numbers, and then the question is like, how far? Okay, so then I go through, and each and every time I set up these equations, I make a list of the variables. And I make the list in the exact same order every single time. And by making a complete list every single time, it should help eliminate me forgetting one. If we look at the units of the numbers that I just highlighted, and we compare that to the units that we wrote down, we can then kind of put some pieces together and hopefully fill in the information. So she was going 15 meters per second, meters per second, meters per second. That's a unit for velocity, and it's either going to be a VI, VF, or V average. Now let's just take a quick look. Is there anything in this problem that talks about average speed or average velocity? No. Don't use equation number 1 then. Okay, so now we're on 2 through 5. 90% of the time that's where we're going to be. Don't use equation number 1. Okay, so now we got to decide, is that 15 meters per second, is that how fast she was going initially in her car? Or is that her final velocity in her car? That's her initial, right? She was going 15 meters per second, then she stepped on the brakes, right? So initially she's going 15 meters per second. Meters per second is a velocity. That's how fast she's going initially, or at the start. Let's look for more numbers. 2.5 s. S is a second, unit of seconds, which is a measure of time. So my time is 2.5 s. Now be careful with your s's. If you put s there, sometimes my s's look like a 5. So make sure that you keep them. It's not 2.55, it's 2.5 s or 2.5 seconds. Just kind of be mindful of that. That was my measure of time. The question of how far, oh look, how far is generally what we ask when we're looking for displacement, and then we just have to decide, is it in the x direction or the y direction? And for now we're talking about a car driving, so hopefully the car's not going this way, hopefully the car's going this way. So we're going to talk in the x direction, and we'll change that when we get to it, but we don't need to yet. So that's what we're trying to figure out. That's my question mark. And I actually put a question mark in my list of variables because it kind of forces me to say that is what I'm solving for. Now, on this list of equations, all of these have 4 variables listed. This one has 4, 4, 4, 4. They all have 4 variables. In order to solve algebraically a 4-variable equation, we need to know 3 out of the 4 numbers. We need to know 3 out of the 4 variables. So sometimes a number is implied or is given without being directly given as a number. So is acceleration or final velocity given in this problem without specifically saying the number? My final velocity. And what is it?
0.
Why is it 0? Because she comes to a stop. Stop tells you a velocity. It's a number. It's 0. Her final velocity, when she steps on her brakes, she comes to a stop. That's her final velocity. So we're giving you a number without directly giving you the numerical value. Is there any mention about an acceleration? Does it ask you about an acceleration? So when I talk about this, I said, do we know acceleration? Do we care about acceleration? And if the answer is no, I cross it off. Now, by crossing it off, it does 2 things. One, it eliminates that little thing on my variable list. Now I know 1, 2, 3 out of 4, right? I need to know 3 out of 4 in order to solve for the 4th. But the thing that I crossed off helps me pick my equation. And there should be an equation that we just crossed off an A, and if we look at our list of equations, there's one equation that doesn't have an acceleration in it, and it's equation number 5. Right? It's equation number 5. So we don't have an acceleration, we don't care about acceleration, so if we use equation number 5, we're going to be okay. Until we get enough practice, people will commonly try to choose equation number 2. We don't know delta x. Equation number 2 doesn't have a delta x. We should choose that one. The problem with choosing equation number 2 is you aren't going to be able to solve for the delta x because it's not in the equation itself. You'd end up solving for the thing that we crossed off and we said we didn't care about. We'd solve for acceleration. So we're going to choose equation number 5. Now, even after doing this all these years, I still do what I'm about to tell you you should do. When I make answer keys, I actually go through this step, even after all these years. When I go through and I said, hey, I'm going to use equation number 5, I actually write down equation number 5. I write down the number 5. And then right after writing number 5, I write it out exactly the way it's listed on my formula sheet before I put in any numbers. And you say, do I have to? I really think you should. Do I have to? I really recommend it. Do I have to? No. But I really think you should. I really think it's beneficial. That's why I still do it after all these years, Could I do it without it? I could, but it eliminates a lot of silly mistakes along the way. So it's a good practice to get into. Because now that I make sure, yep, I wrote that equation correctly, now I'm just simply taking numbers from my list and I'm putting them in there. Order of operations, all apply, parentheses, squared, multiplication, division, addition, subtraction, all that good stuff. We still have to follow all those things. But now we can start plugging in numbers. Delta x is my unknown, that's what we're going to solve for. My final velocity is 0. Anytime I have a 0 in my list, I like to go up to my original equation, and I often will do something like that. I'll cancel it out up in the original equation, because it's 0 and has no value. Now it's up to you and what you want to do. Sometimes people like to put that 0 still in there and say, well, 0 plus my initial velocity of 15. Some people like to do that. Some people just like to say, well, do I have to do that? Can't I just say it's 15? And the answer is yeah, it's because 0 plus 15, it's 15. So it's really up to you. I'm going to do it like that for today, but probably in the near future, I'm not going to do that. So delta x is equal to 0 plus 15 divided by 2 times 2.5. So you got to do your addition first, so 15, then 15 divided by 2 or multiply by 2.5. It really doesn't matter the order in which you do. But I'm going to say this is 7.5 times 2.5. And then when you plug this into your calculator, your delta x is going to be 18.75. Now you notice how I put units here, and that came from my problem. Help me identify this. I didn't put my units in my equation, because that just kind of makes it messy. So I only put my numbers in my equation. But an appropriate answer has a unit associated with it. Now if we go over to this list, if everything I used had these units going in, I'm going to get all of these units back out for my final answer. So because I only use meters per second, and I only use seconds, then my answer is going to come out in the units of meters. So my final answer is 18.75 meters. That's how far that car is going to travel in that 2.5 seconds. Okay? I want to take a look at a different one. I'm going to look at number 6. I'm going to jump around a little bit. We're going to take a look at problem number 6. Now number 6, one of the reasons I want to look at number 6 is there's numbers there that we kind of got to pull on some maybe everyday life or past experiences or kind of think it through. So some of you I know have flown, some of you have not, but if we kind of think about an aircraft going down the runway, we can kind of answer some of these questions. So an aircraft has a liftoff velocity of 33 meters per second. What is the minimum constant acceleration required for an aircraft to take off in 240 meters? So it's an airplane going down a runway. It has a velocity of 33 meters per second. What is the acceleration? That's my question. And then 240 meters. Those are the numbers that are given, and that's the question being asked. Now, the wording of the question, don't get hung up on. It says, what is the minimum constant acceleration? All that's saying is, what is the smallest value that we can have? What is the minimum? What is the smallest value for my acceleration that we can have? And the fact that it talks about constant algebra, it's not calculus. Okay? So using these numbers, meters per second, velocity, meters per second, 240 meters, what is the acceleration? Those are the numbers that are given. So if we go to our list, liftoff velocity of 33 meters per second. We have a plane who's going down the runway and they're going to lift off. They're going to fly. Fingers crossed, they're going to fly at the end of the runway. In order for them to lift off, they have to be going 33 meters per second. Now, if we're talking about the plane going down the runway, is that meters per second, is that velocity how fast they're going at the start of the runway initially, or at the end of the runway, their final velocity? Their final velocity, right? So their final velocity is that 33 meters per second, sorry, that 33 meters per second. That's their velocity, their final velocity at the end of the runway. That's how fast they gotta go in order to start flying. The question being asked is, what is the acceleration? What's A? And required for the aircraft on a 240 meters. Meters is a displacement. That's a delta X. I only have two numbers and one question mark. I need one more number, and it's either going to be given in the problem or it's implied. Now, this runway problem isn't perfect because if you've been on a plane, I've been on not a lot of flights, but I've been on some flights. And sometimes when the plane is taxiing out to the runway, sometimes the plane goes and then they turn and then they like stop. And then engines, and then we start to go down the runway, okay? But sometimes they're turning, they're taxiing, and then they get there, and then they just turn and go. And they don't do that stop. So it's not perfect. But if we think about it, what's the initial velocity at the start of their runway? It's meant to be 0, okay? It's probably the one that I like the least in terms of being an implied value. But we're going to say it starts with a 0 velocity because they can make that turn. Now you could make the argument because they're going like this, that's the Y direction, and they're not moving in the X. I agree. But we're going to just go with a 0. Does it make any reference or mention of time? Anything with seconds in it? Do we ask about time? Okay, so we can cross that off. Now when we look at our half sheet and we start picking out our equation, we say, okay, what equation doesn't have time in it? And if we look at equations and we say, doesn't have a time, hey look, equation number 4 doesn't have a time in it. And equation number 4 is VF squared is equal to VI squared plus 2 times A times delta X. I use parentheses a lot for my multiplication symbol. Realize here there isn't, but it's 2 times A times delta X. That's what that's saying. Now, quick mathematical review, nothing to do with our exact problem here, but what is the square root of 4? I'm going to erase this in a second. This has nothing to do with this exact problem. What's the square root of 4? 2. Partially right. What's the more mathematically correct answer? Plus or minus 2, right? Because a negative 2 squared is 4. Positive 2 squared is 4. Okay? So anytime we take the square root, remember mathematically it's plus or minus. Now why am I saying that? Is because in equation number 4, there are some squared terms. So there are some times we will have to take the square root, and then you're going to have to make the choice, was it the plus or is it the minus? And I'll help you kind of figure those out when that time comes. That's not this problem right now, so we don't have to worry about it. Just kind of planting that seed for down the road. So using equation number 4, we're going to solve for acceleration. My final velocity is 33 squared. My initial velocity was 0. And like I said, I often like to go through into my original equation and I like to cancel out that term ahead of time because it's a 0. Now it's up to you whether you go 0 plus. A lot of times I won't. I'll just say it's going to be 2 times A times 240. Okay, now if I remember from last hour, I believe 33 squared is 1,089. 33 squared, 1,089, yes. Which is equal to 0 plus, I'm just going to get rid of that 0, 2 times A, 2A, times 240 is 480A. I'm going to say that again. It's 240 times a. And the reason I said it so loud is just to be very clear, it's 240 times a. What is the inverse function of times? Dividing. So how do we isolate this a? What's the next mathematical thing we must do? We must divide by 480. I'm going to divide both sides by 480. And we get a value of, I don't even remember, divided by 480. It's a long decimal. It's 2.26875. Now, I told you that I don't really care about sig figs. I'm going to say that so loud, chemistry teachers in here. And generally, I'm going to say let's round to that second decimal point. So because of that, I can say it's 2.27 meters per second squared. Now, the reason I can say it's meters per second squared is because I used meters per second, I used meters, I used all of these units. So because I used all of these units, my units are going to work out to be meters per second squared. What that says is that 0 seconds is going 0. At 1 second, it's going to be 2.27. 1 second after that, it will be now going to 4.54 meters per second. It will have added 2.2, and then add another 2.27, another 2.27, until it's going 33. That's what an acceleration is. Remember, we need directions. It's implied that it's positive, so positive means it's moving to the right.